This diagram is the proposed design for the CPU architecture in which I am going to use to implement and explain the HDL code of the CPU. In the following diagram, the CPU consists of several logic gates such as the ALU, A register, D register, PC and the multiplexer. Since we have built most of these logic gates from the previous tasks in the unit, it will be easier to implement the CPU HDL code with them. The first step to implement the code is to derive the API of the CPU. The API specifies the chip name, the input and output pins, and the function of the CPU, and an additional comment. So for now, let us not think too much of the logic gates inside the CPU chip and start off with an abstraction of this chip by hiding all the logic gates in this diagram so that we can easily identify the input and output pins of the CPU. Now we can clearly see the input and outputs of the CPU as shown in this diagram. There are three inputs coming into the CPU from different sources in the computer: the instruction memory and the data memory. These inputs are the instruction, INM and reset. The instruction input is from the instruction memory, which is the value of the selected instruction memory register. This instruction can either be an A instruction or a C instruction. On the other hand, in INM, the value of the currently selected data memory register and is the value that the CPU uses to perform its operations. Here we can really see a diagram that further shows the CPU is connected to the instruction memory and the data memory. This diagram was used to implement the hack computer in one of the previous tasks. Here we can really see that the CPU takes its instruction input from the instruction memory and also takes the value of the selected data memory register as one of its inputs. The reset input is a value that tells whether we bring the CPU back to its initial state or to be specific to the start of the operation of the CPU all over again. Furthermore, along with the inputs, CPU has several outputs that are connected to the instruction memory and the data memory as well. These outputs are called as write M, at M, address M and PC or the program counter. Going back to the given CPU architecture, we can see that the ALU gives an output that is written to the data memory. In order to do so, the ALU must specify a few things. First, the content that the CPU is going to write into the data memory, which is stored in the out M. Second, the address of the write operation in the data memory. Basically, this is where we want to put the content in the data memory. Lastly, the output that allows CPU to write the content to the data memory. Write M. The program counter holds the address of the next instruction, which will then be fetched, decoded and executed by the CPU in the next cycle. Now that we have identified the inputs and outputs of the CPU architecture, we can now implement the code of the CPU. This is the HDL code of the CPU that was provided in the task resources. I'll explain this code to you in more detail by parts as I go along with the presentation. Here we have the header section that specifies the CPU interface. It consists of the chip name and the names of its inputs and output pins. Since we are implementing the CPU chip, the chip name that we are going to write for this code is CPU, as shown in this code. The input pins of the CPU will consist of 16-bit NM, 16-bit instruction and reset. On the other hand, the upper pins of the CPU will consist of 16-bit out M, write M and 15-bit address and a 15-bit PC. The input and output in this header section of the CPU do correspond to the design that was shown and discussed in the previous slides. This is the first part of the part section in the CPU HDL code that I've shown previously. As you can see that we have three different gates: NOT gate, AND gate and a MUX16. These gates allows the CPU to function and perform specific operations. Firstly, there are two types of instructions coming into the CPU from the instruction memory. These instructions are the A instruction and the C instruction. Here I will explain the A instruction and the C instruction in more detail. A instruction has a symbolic syntax of add value. This value can either be a number, that is a decimal, non-negative number, or a symbol. If the value of A instruction is a number, then the instruction will set the contents of the A register to the specified value in the instruction. If the value of the A instruction is a symbol, then the instruction will set the contents of the A register to the value that the symbol points to. And this value will not be the actual value in that memory register. On the other hand, C instructions has a symbolic syntax of text equal to comp and jump. And this instruction performs the computation on the CPU, which is stored into a destination register or a memory location. It can also tell us the CPU to which other instruction memory address that is pointed by the value or the symbol. In the first line, we can see that the NOT gate is used to tell whether an instruction coming into the CPU from the instruction memory is an A instruction. But first the CPU decodes the 16-bit instruction into an opcode and a 15-bit value. If the opcode is 0, the instruction is an A instruction. Whereas if the opcode is 1, the instruction is a C instruction. For instance, if the instruction coming into the CPU from the instruction memory is an A instruction, the CPU takes the specified 15-bit value and stores the value into a A register. However, as you can see in the diagram that was taken from the CPU architecture, that the A register can be fed by either the instruction input or the ALU output. If this is an C instruction, it performs the computation in the ALU, and the ALU output is fed to the A register. We can use AND gate to determine that the instruction is C instruction. A 16-bit multiplexer is also used to select whether the instruction or the ALU output is stored into the register A. In the next part of the code, we have an OR gate. The load bit in the register would be 1 if either the A instruction or the ALU output is fed to A. On the other hand, the A register is used to store the value that is fed into the A register. It takes in the output A register from the multiplexer and the output load A from the OR gate as its inputs. The output A out then generates the content or the value that is currently stored inside the register. Next, in the other mux16 gate, which takes in the output of the A register and the value that is currently selected in the data memory. This will select which one to output, or M. Either A or M will fed into this instruction will depend on the 12-bit instruction value the AND gate is employed to find out whether the ALU output is loaded into D register. The D register is then implemented to load and store the value of the D register from the ALU. Next up is the ALU gate. The ALU comprises and computes a function of two inputs, which in the case would be the value that is stored in the D register and the value of OR M register. Then generates output. It consists of input control bits such as ZX, NX, ZY, NY, F and No, which are the indicators of which function is computed on the two inputs to produce output. Whereas the output control bits such as the ZR and NG determine the properties of the result. The following code, which consists of 2 OR 16 and an AND gate, sets the ALU outputs in order to successfully write on the data memory. The first OR 16 code line determines the address of write operations. The second one determines the content of the data memory. And lastly, an AND gate that outputs a value that allows CPU to write the contents to the data memory. The program counter, or also known as the PC, is a register which contains the address of the instruction to be fetched next. In this part of the CPU HDL code, the load bit of the PC is determined by the jump bits and the ALU outputs. Basically, these lines of code determines jump conditions and checks the ALU output to see if the conditions are met. If the instruction is C instruction and the conditions are met, the program counter is loaded with value that will ask the CPU to jump to the specified value or symbol. If the PC is not loaded, then PC is incremented. Incrementing means that the CPU will read the next instruction. So this is how I understand and will implement the HDL code for the hacked CPU. Thank you for listening.